Okay, so for this example, as promised prior to this, we're going to look at how much or how many bytes does each variable occupy based on the type that you've assigned for that variable. Okay, so that's going to be important. And where in memory is that variable stored at? Okay, so now let's go ahead and start with a simple example of declaring it a simple integer and then looking at two things about it. How many bytes that integer will need to be expressed. Okay? And remember, a byte is 8 bits, right? And then after that, where in memory might that variable be stored at? Another concept that I want to talk about too is, where did you declare this variable? Now remember, last example, we declared a variable within main. int num1 right here, right? So we've declared this variable here. So we know this is a declaration. So this is a variable declaration. I'm going to add one more concept. This is a local variable declaration. Local to what? Local to this function. Aha. So that means, can we declare a variable outside of a function? What function? Main, right? So can we declare something outside of main? Absolutely. You could do something here. Int num2 semicolon. This here will be called a global variable. Now, that will have an importance later on in terms of why we would declare something global versus why we would declare something local. And it will have to do with the scope or the lifespan of a variable. So that's another attribute we need to discuss in the future in terms of, okay, we know the size, we know where it's stored in memory, but what is its lifespan? Does it live throughout while the program is running, or does it only live while certain functions or within a certain function while that function stack is alive? And so do we have different spaces in memory where we store this kind of variables, global variables, local variables? I mentioned the word stack. Yes, so we're going to learn about stacks and heaps as we move forward through these lectures. Okay, so I'm not going to get into stacks and heaps yet, but just realize that you can declare something outside of a function and you call it a global variable. And then you can declare something within a function and call it a local variable. Let's focus on that local variable num1 and find out, for example, how big is it? How many bytes does it occupy? Okay? And then where in memory is it? Can we actually print these attributes? Absolutely. You could do something like this. Cout. The number of bytes needed for num1. And then you could use a function called sizeof. Now, we didn't define this function ourselves. It's in the standard library, so it is for us to use. Sizeof. Notice it's a keyword, and it takes a parameter, and within that parameter, it's a function. The actual parameter, or the parameter value, is actually num1. Okay, so that will be the argument that it will take, and then endl, and that should give you how many bytes this occupies. So let's compile and run this and see how many bytes num1 occupies. Now notice I didn't put any data in num1. Okay, all right, so compile and run, and there you have it. So the number of bytes needed for num1 is 4 bytes. Okay? Perfect. Can we see where in memory is it stored? Now, at this stage, it will randomly pick a memory location for it, but typically it will be at the bottom of the heap. I mean, at the bottom of the stack. But let's not worry about that. Later on, we'll learn how your operating system and your computer and your application work together to allocate memory. But right now, we just want to know where in memory is it. So the address for, I would say, to be technically correct, you should say the starting address, not just the address, because it takes 4 bytes. Okay, technically each byte has an address in RAM. Okay, so that's typically how it works. But by saying the address of num1 is, this is going to give us an address. But to do this, you can't just type num1, otherwise it will be the content of num1. You're going to do this, and %num1. So and %num1 means the address of num1. Okay, well, let's see if we do get an address. Typically an address, okay, will be expressed in hexadecimal value, as a hexadecimal value. Well, let's see if that's true. Compile and run. And sure enough, here he is. So we have 22FF44. So this is the address where num1 starts or stored, and then it takes 4 bytes from there, from this number. Okay? All right, so, and again, we're going to see in the future, does it subtract 4 bytes from that number, or does it add 4 bytes to that number? And again, that's a totally different lesson. That's when we get to understand how memory is organized. Right now, I'm just concentrating on these two. Now, if I try to do this, cout. Now, we've seen this example. The content of num1, and you put num1 here, and L. Now, what would we get? We will get whatever garbage was in there. We've seen that from the previous example. So let's go ahead and run it. Compile and run. And sure enough, we get some random value, right, for num1. Let's see again what we just did here. We wanted to peek into what's in num1, stored at this memory location. And it took 4 bytes to store this number. Okay? And that's, if you had to read it as a story, that's what it's telling you. The size of num1 is 4 bytes. This is the starting memory location where num1 is stored in RAM. And this is the content of what's in num1. Now, again, as I told you before, it's always a good idea to either initialize num1 or ask the user to put a value in it, or actually at compile time put a value in that num1. So let's do a compile time assignment. So num1 equals -2. We could do that. So num1 has a value of -2. So this here is an assignment, right? And let's see if we get our -2 here. We should. Nothing else will change there except for the memory address might be randomly picked again. But we'll still need 4 bytes to store -2. Now, is 4 bytes enough to store -2? Yes, it's overkill. If, let's say, you were dealing with numbers from 1 to 10 or something like that, then sometimes just a regular integer might be too big in terms of space to store just small numbers if you're counting from 1 to 10. So is there an alternative? Answer is yes. You could do what we call a short int. And let's do the same example now with a short int. So all I have to do is change this int into a short int. Now let's see if things will have changed. So I'm not going to change anything here other than num1 now is a short int. Let's see what do we get. So compile and run. And notice now, for a short int, I only need 2 bytes. Okay? 2 bytes to store a short int. Okay? And this is the address right here for the starting byte of these 2 bytes. They're occupied in memory, reserved in memory, to store the value -2. Now, somebody might say, is there something as a short int? Now, watch what happens when you compile this. And you get an error. So no, you're not going to go into a short int. All right, so leave it as short int. Let's recompile. Okay, so as you can see at the bottom, it says duplicate short. That means it's not part of the lingo. It's not part of the language, right? So compile and run. Now we're back in business. All right, so short int is the lowest you can go there, right? So short int means 2 bytes. So that's 16 bits if each byte is 8 bits. Still, right? But for modern computers, that's not a big deal. So if this was a robot and you don't have a lot of space, short int is probably a good idea to go for, since your RAM chip might be a little too small. It's not, you don't have the flexibility of a PC to upgrade your RAM even more, right? So just simplistically speaking here. All right. I hope you got the idea here. Now, what if I went for a long int? How many bytes will that be? Let's go for a long int. Compile and run. Notice my long int is still 4 bytes. Now let's go for a long int. Long int. Let's compile this. Compile and run. And this time is 8 bytes. Okay, to store that -2. Okay, now remember this memory location is randomly assigned to this variable. But this is just a peek to see where in RAM, right, is it stored at. Okay. All right, so what if we change num1 now to a float? Let's see what the effect of a float will be for us. Okay, so compile and run. And float is 4 bytes. Now with floats, you can have values like this, -2.5. And that shouldn't be a problem. Compile and run. Now, if that was an integer, then it will truncate it. So if this was an int, so that means I am forcing a float into an int. Notice the compiler does not worry about it, because what's going to happen, it gets truncated to a -2. Okay? So what you've done here is you've basically typecasted into an integer. Right? So what if it was higher than 2.5? Let's say it was a 2.8. Let's see if it rounds it up or simply truncates. Compile and run. As you can see, it simply truncates. It doesn't round it up, so be careful with that concept. Okay? And again, if you did 0.001, same deal. It will truncate for you. So compile and run. Okay, to -2. Okay, so if you had, for example, 0.999, right? Let's see if it truncates to 0. Compile and run. And sure enough, it truncates to 0. That's because we forced a float number into an integer. Okay, so now let's put it back to float. So this should be handled by a float, no problem. So compile and run. And that's not a problem at all. Now, what if I had a double? All right, so we're going to look at double now. Now remember, your float was 4 bytes. Let's see how many bytes are for double. Compile and run. And now I have 8 bytes. right? So what if I needed much, much larger numbers to handle much? So the more bytes you have to express a number, the more bits you have to express that number, which means you can express higher numbers, right? Especially in computations where you really need huge numbers. So what do we have? We have long doubles. So let's go ahead and do that and see if we get more bytes, which means more bits, right? And let's compile and run. And sure enough, I get 12 bytes reserved for long double. Okay, so I hope this helps you understand the different flavors here required for these. Now, great. So what if num1, let's say num1 was bool, right? And let's say num1 is true. Now let's see what a Boolean variable, what is its size, and what is its content. Now it's true, we've seen that before, it's 1, right? But let's see how big or how many bits are reserved for that Boolean variable. All right, so compile and run. And notice now it's 1 byte. That's all you need. 1 byte, right? Remember, a simple int and a short int were 2 bytes. But now I only have 1 byte reserved for a Boolean. Okay? Right, so 1 byte is from 0 to 255, by the way, unsigned. So what if I went for a value of 345? Right? So what would happen? So compile and run. You would get a 1. It's beyond so you have a 1 somewhere in that byte, right? So you're going to get a 1, which is true. Even though that number is expressed higher than a byte. But we're not looking at 345 as a value. We're just looking at the fact that there is a value stored in there. Okay? Which means it's true. Great. So now, what about a char? So what if I had a char here? I could call it num1. But if it's a char, I'm going to store now a character in there. And let's say the lowercase d is stored in there. Okay, so let's see how many bytes a char will need. Okay, and as you can see, num1 will simply display the character that we have there. So compile and run. And notice also a character takes 1 byte. Okay,